In biological systems, photosynthesis and cellular respiration are redox reactions. While it is true that photosynthesis is an endothermic reaction requiring energy to proceed, as we shall soon see, the photosynthesis reaction and cellular respiration is a reaction that involves the movement of electrons from the reducing agent to the oxidizing agent. From earlier definitions, the glucose is oxidized by the oxygen and is thus the reducing agent. All hydrocarbon combustion reactions are redox reactions. This picture of fireflies from your text is another biological example of a redox reaction. Light is one of the products. Shown just below this picture are the molecular diagrams of the reactant and products, and as you can see, there does not appear to be any metals involved. How would you write the half reactions for this one? Well, sometimes it's not easy to see if a molecular reaction is a redox reaction. This is where oxidation numbers come into it. In general, oxidation numbers are assigned to atoms in a molecule or compound. Ionic compounds are easy. Take sodium chloride. When dissociated, we don't see sodium metal and chlorine gas appearing where each atom has a balanced number of protons to electrons. The metal loses its valence electron to the nonmetal. This causes the metal ion to have more protons now than electrons, and so is positive ion. Specifically, the sodium metal gives up one electron and its charge is positive 1. The nonmetal gains the electrons, meaning that the nonmetal atom now has more electrons than protons, making the resulting ion negatively charged. With chlorine here, sodium's valence electron is added to chlorine's valence electrons. Chlorine now has one more electron than it does protons, and so it has a charge of negative 1. The oxidation number for the sodium atom is positive 1, the same as the ion charge, and the chlorine atom is negative 1. For this compound, its neutral charge can be easily referenced by the sum of its oxidation numbers. Positive 1 plus negative 1 equals 0, the net charge. Potassium sulfide is another compound with a net charge of 0, so the sum of the oxidation numbers will also equal 0. The sulfide has a negative 2 charge, and while the potassium ion has a positive 1, there are two of them, adding up a net positive charge of 2. Each potassium ion having a charge of positive 1 has an oxidation number of positive 1. The two potassium ions together yields a net positive charge of 2. The sulfide has an ionic charge of negative 2. There is just one of those, and so the oxidation number for sulfur is negative 2. Potassium sulfate, also an ionic compound, is complicated by the presence of a polyatomic anion. The potassium ion still has an oxidation number of positive 1, so there is a net positive charge of 2. But it's the sulfate ion that has a net negative charge of 2. But what are the oxidation numbers of the sulfur and oxygen atoms within the sulfate ion? Is the sulfur atom not negative 2 like the compound just above it? The sulfur atom has an oxidation number of negative 2 when it's a sulfide. When it's part of a molecular compound, including polyatomic ions, it may have a different oxidation number. Is it possible to determine the oxidation number for the sulfur atom in a sulfate ion? It is, but first we have to remember a few rules. Rule number 1, the oxidation number of an element in the monatomic ion equals the charge on the ion, and this follows the previous examples. An oxygen ion, as found in iron 3 oxide, for example, has an oxidation number of negative 2. The aluminium ion in aluminium nitrate is positive 3. Rule 2, a pure element has an oxidation number of 0. The number of protons equals the number of electrons. There's no net charge. Even in diatomic and polyatomic elements, electrons are shared equally between the atoms. So there's no net loss or gain of electrons. The oxidation number is 0. Rule 3. The oxidation number of hydrogen in molecular compounds is positive 1, and in ionic compounds is negative 1. Some molecules, such as ethanoic acid, CH3COOH, have hydrogen atoms all over the place. But each hydrogen atom has an oxidation number of +1. To know when the hydrogen is a hydride with an oxidation number of -1, the hydrogen always follows a metal ion. The reason for this is that in molecular compounds, the hydrogen atom is not usually the most electronegative atom. So when covalently bonded to a more electronegative atom, hydrogen tends to generate a partially positive charge as its only electron is drawn closer to the nucleus of the more electronegative atom. Rule number 4. The oxidation number of oxygen in compounds is -2, and in peroxides, -1. In ionic compounds, the oxide has a -2 charge. In molecular compounds, oxygen usually has the strongest electronegativity in the compound. That is, oxygen will attract the shared electrons more strongly. We assume then that to create oxygen's oxidation number, oxygen is assigned the shared electrons. In the case of water, for example, oxygen is assumed to take both of hydrogen's electrons like an ionic compound. In the case of peroxides, there are only 2 electrons being offered, the 2 given up by hydrogen in this case, and so each oxygen atom gains 1 electron, thus an oxidation number of -1. What if oxygen is paired with a more electronegative atom? Oxygen difluoride is the only case, since fluorine is the only atom more electronegative than oxygen. Oxygen then loses an electron to each of the fluorines, giving oxygen the oxidation number of +1. Rule number 5. Molecular compounds not containing hydrogen or oxygen, the net ionic charge of the more electronegative element is the oxidation number of that element. In nitrogen trifluoride, the oxidation number of the more electronegative element, fluorine, is the same as the ionic charge, -1. Rule number 6. The charge on the compound equals the sum of the oxidation numbers of all the atoms. The sum of the oxidation numbers of all the atoms in a neutral compound is 0. In a polyatomic ion, the oxidation numbers should add up to the charge of that ion. It's this rule that helps us apply oxidation numbers to atoms not included in our rules. The rules should be memorized. Practice in assigning oxidation numbers to atoms of compounds and polyatomic ions will certainly help.